useless. Guys, can we all remember to do this so everyone sees it? Please. What is that? Ridiculous, Emily. All right, guys. Just wanted to make a quick note that your exams, from the time that you get them back, you have 1 week to discuss any concerns you have about grading. Sometimes points don't get added up right, or you don't feel that grading was fair on a particular question. You have 1 week to bring those to my attention. After that 1 week, your grade is confirmed. It is going to stay that way forever. So don't try to come at the end of the semester and realize you need 3 points in order to have a different letter grade and then discuss it then. I will not discuss any exams at that point. Make sure all the points add up properly, that they're graded fairly, and that everything looks right. McKenna, is the key online? Okay, so I should have the key online. If I don't, I'll post it. So you should be able to see the questions and use that to make sure that everything looks good. Any questions about the exam? You guys have, what, 2.5 weeks until your next one? The 28th of October, Friday the 28th. If you guys want to dress up, that'd be awesome.
Dress up?
It's kind of Halloween, right?
I'll dress up. Oh.
Like it. All right. Okay. So you guys have been spending some time outside of class thinking about how different terms in kinetics relate to each other, right? You guys were doing concept maps in lab yesterday and today. So today we're going to expand on some of those and try to make sure that you guys are able to use integrated rate laws and compare them to differentiated rate laws. McKenna, you have any questions? McKenna, you good?
No.
Okay. So I want everyone to look at this data and then click in whether it's 0, first, or second order. Talk to your neighbor. Try to figure out what more information you'd want in order to answer this question.
I said that it was second order because if you look at the time, it's going up in intervals of 5. And if you look at the concentration, it's going down like at an exponential rate.
A couple more seconds. Who are you sitting with?
I talk to these people.
Okay.
I just called you these people.
Brianna, can you share your thoughts? What you saw when you started looking at this?
So I looked at the time first, like the interval of the time, and it's going down in intervals of 5 seconds, or going up in intervals of 5 seconds. And then I looked at the concentration to figure out how much it was going down every 5 seconds. And it's not going down at a constant rate, it's going down like at a different number every time.
I love it. So what you did is you said, well, you're kind of plotting it in your head is what you're doing in one way. Is you're saying that I noticed that the time change, we're starting a reaction, then we're looking at it every 5 seconds, or 5 minutes or whatever. I didn't include the units here. We're looking at it every 5 time units. If we had the same change in concentration between 0 and 5, 5 and 10, 10 and 15, 15 and 20, what order would that be? Does everybody agree? First order. Which order does the concentration not affect the rate of the reaction? 0 order. So we can definitively say that this is not a 0 order decay process. What questions do you guys have about that? If it was 0 order, we'd see a change of 28.6 for every 5 of these time units. Is there another way we'd want to look at this data to better be able to decide whether it was first or second order, though? What would you guys want to do with this data in order to get some more information about it? Okay, so we can have units. I don't know that that would necessarily give us more insight into what the rate order is, but it would tell us more about the reaction. Javante? Okay, so we could graph this, and then we could see whether it was this kind of shape or it was this kind of shape. And based off of that, we'd be able to get an idea if it was first or second order. Thomas? So each one of these? So we could take those and plot them and look at them that way, you mean?
No, just like subtract. So like the last two, 18.5 minus 17.2.
Yeah, so we could do 28.6 for this difference. This one is, ooh, what is that? 1016.2. This one is 10.9. We could look at the differences. So how did that help us?
So it's not going down proportionally, it's going down exponentially.
Okay, so there's some difference it's going down, but proportional, we're talking about, is the rate proportional to the concentration? And so that we'd have to do a ratio of those two, which gets a little complicated. Any other ideas of what we would do? Kristen?
Would you do the natural log concentration, or do the, I guess, the inverse, the 1 over concentration, and then see which one's in your line?
So can someone pull out a calculator? All right, can you type in, what's the natural log of 100?
4.61.
What's the natural log of 71.4?
4.27.
55.6?
4.02.
Okay. Can someone else calculate 1 over the concentration? So 1 over 100? 1 over 71.4?
0.04.
1 over 55.6?
1
Zero.
or 0.
Go ahead, Brian.
0.017.
Okay, and we can do that for every single one of these data points. Why would we do that? Kristen, what do we get out of that?
I can graph it if it's linear, or if it's a line that's going down proportionally.
What are we going to graph? What are our 3 plots going to have on them?
The concentration versus time.
Okay, so the first one is going to be concentration versus time, and it might look like one of these two. We're not sure which. Okay, what's our next plot going to be? Shane? We're going to do another plot of ln of the concentration versus time. And then third one, we're going to plot 1 over concentration versus time. We're not making up any data, right? We're just saying, well, maybe there's a trend that we can infer instead of looking at the 2 graphs I have on the left, which would be concentration versus time. We're not sure which one of these 2 it is, and those 2 look fairly similar. Have you guys noticed the first order and second order? They both kind of have this swooping effect. One swoops deeper than the other. That's exponential. Proportional is a little bit less steep of a swoop, but it's hard to tell. So if we actually do the calculations, and these are the numbers that we started calculating. We did the first couple in each, right? I just wanted to show you these numbers weren't made up out of thin air. And then we take all of these and we plot 1, 2, and 3. So we're going to end up with 3 graphs for every reaction that we're monitoring. And we're going to start to see some trends when we do that. So you want me to show you those plots? So what information do we get out of this? Concentration versus time, that's the one shown in the middle. That has obviously not a linear decrease. So what can we tell from the middle graph? What does this graph tell us? Dan? Yeah, what does that graph tell us? What can we immediately say about the rate order of this reaction? Tatiana? No, we can't say it's exponential. We can't say it is something in particular yet. We can say it's not something. What does that middle graph tell us it's not? It's not what? Careful. When we say proportional, we mean that the rate, the slope of the graph is proportional to concentration. That doesn't mean that it's a straight line. Taylor?
You mean that the rate order is greater than 0?
It's not 0 order. It has to be something else. So I'm hearing from a couple different people that if you had a graph like this, that you would say that the rate is proportional to concentration. That is absolutely not the case. How does the rate of the reaction change with concentration with the straight line for concentration versus time? Is the rate of reaction different at the two places I'm pointing the arrow at? No. Is the concentration different at those 2 points? Yes. So if it's zero order, that means that the concentration does not affect the rate of reaction. That means it's not proportional. When we say proportional, it means that the concentration is proportional to the rate of reaction. Okay. So we can say from the middle graph, concentration versus time, we know this is not zero order. Then how do we use the other two graphs to tell us whether it's first or second order? Chase?
We see as the concentration goes down, if this, like increment-wise, if it goes down by the same rate as you go down the concentration, to see if it's first order. And if it doesn't, if it like decreases more, decreases less, it would be second order.
Okay, so I think you are focused quite a bit on the individual changes between each data point. But I want to use the other two graphs to make it way easier than that. I want to take this data that we plotted, we calculated, right, the natural log of whatever that concentration was at each time. We calculated 1 over the concentration each time, and we ended up with these plots. So how can we use the plot on the left and the right in order to tell what rate order this reaction has? Jose?
No, I'm pretty sure it is second order.
This is second order. How do we know that?
I want to say it's something because kind of the graph is linear, and the second order, when it's compared to whatever concentration.
Okay, Cosmo, you want to add to that?
The one on the right, the derivative.
So all of these, the left and the right, are based off of using calculus to look at the area under the curve for different plots. And based on the calculus that we're not going to use in this class, that these relationships will tell us whether it's a first order or a second order. Thomas, you want to add to that? Are you holding your hand up, or are you just... Okay. So the simple view of it is, if you guys know that we can take those data points and we can make a new xy, so here the xy is time versus concentration. If we can plot the 1 over concentration versus time, natural log of concentration versus time, only one of these is ever going to be a straight line. And we'll talk a little bit more about that in class today and what information we can get from that straight line. But that allows us then to back out and say, well, I can see that we have a linear relationship between 1 over concentration and time. I know that that is second order. How does that help us? Why do we care if a reaction is second order or not? We know what the units of K are. Great. What else? Taylor?
Doesn't that kind of tell you how fast it's going to be used?
It allows us to predict the rate of the reaction when we're at certain concentrations. Fantastic. And there's one other thing. What else does the rate of a reaction, or the rate order of a reaction, allow us to do or know about that reaction? Javante? So they may or may not relate to the stoichiometric coefficients. Remember we said if it was only one step, then it can relate. But we also don't know that it's one-step reaction. Michelle?
I was gonna say it tells you rate law.
Which rate law?
Like, no, I mean, yeah, the equation.
Which equation?
Like K times A to whatever, B to whatever, or over.
Okay, so the differentiated rate law, and I think that's what, a little bit what Taylor is getting at, that how the rate of the reaction can be predicted based on the concentration. Justin?
Doesn't it predict the integrated rate law?
So once we know it's a second order reaction, we automatically know how the concentration changes with time. So initial versus final concentration, and now time is part of that equation. So differentiated rate law only compares rate and concentration. The integrated rate law now allows us to include time and initial versus final concentration. So we're going to be dealing a lot with that today. And I imagine that this is going to be pretty uniform now. All right, so I want you guys to be able to just look at 3 plots of data. The concentration versus time, natural log of concentration versus time, and 1 over concentration versus time. And I want you to be able to find those data points as well. You guys all know how to use Excel. You all know how to calculate, so you could do this. And then from these, you should be able to determine what rate order reaction is. And then from that, you should now have access to a whole bunch of relationships to how concentration influences rate and how concentration changes with time. We'll also be able to derive our rate constant, small k, from the slope of all of these different graphs. There's a lot of information that's hidden in these graphs. And then, this is going back to the big thing that Morgan had talked about. Morgan is not here today. Which is, how long until we have some overdose is no longer a concern because we've decreased the amount of drug that's in the system. So we should be able to predict the relationship between where we start with in concentration and where we get to. So here's a zero order reaction. Can you guys look at the data in the top right corner and see how you can use Brianna's description to verify that this is zero order? You guys need a reminder of what Brianna said? Brianna, can you state it really briefly? What did you say about looking at a table of data?
What is the ratio between the change in concentration and the change of time?
So with these, there's about, actually the amount of change in time is different for everyone, isn't it? Yeah, okay, it's not very easy to look at. We should be able to say, well, we can look at maybe 10 seconds and 30 seconds. It'd be easier if we did plots though, right? So let's do this instead. If we look at these 3 plots of data, which one of these 3 is the easiest to use to determine the rate order of this reaction? Go ahead and click in your answer. Justin, what were your thoughts?
I was going to say concentration over graph. Because when looking at those two, I think we already said that 1 over concentration for time would determine the second order if it was a linear. And then the natural log concentration over time would be for first order.
So what I'm trying to get at here, and a lot of students get stuck in this, all 3 of them are linear and there's some relationship. That's not the case. When we take this data, the data that I just showed right here, we take that. Sorry about that. Thank you, John.
Thank you.
We take all of that data and we look at which one of these relationships is proportional, would make a linear graph, then we should be able to say that only one of those is ever going to be linear. There's no way that any 2 of these are actually going to have a linear relationship. And what that helps us with is that we can use the differentiated rate law that applies to that reaction now. So the first step is use a graph to determine what rate order it is. And then we say, well, I know it's 0 order, so I know now that my differentiated rate law is always going to be rate equals my rate constant. What's the integrated rate law for a 0 order reaction? Go ahead.
The final concentration equals negative K times time plus the original concentration.
So what is this equation telling us? Why don't you talk to your neighbor for a second. Try to figure out that integrated rate law that I have written there in red. How does that equation, when is that useful to us? Why do we care about that? When would we use it? How is it useful? You want to join your group today? Jump over here and join them? Sure. Thanks, man.
Whatever, and then at 0.
This isn't for 0 order, right?
And then
It is for 0?
and then the K becomes constant, and then what is
Oh.
Gus, I'm going to call on you for one of these coming up soon. Make sure you're following on.
That is linear. ln versus time. Sorry.
Kirk, when would we use this equation? What might it be useful for? Valerie, what are your thoughts? Sarah, are you paying attention?
I'm really confused.
Okay. Who has an idea of when we might use this integrated rate law? Cosme, when would we use this? What would it be useful for?
Isn't it when we know one concentration, figure out the other one?
So let's say that we're going to be talking about binge drinking in studio tomorrow. If you have a peak alcohol concentration in your blood, and I tell you, or you look at a graph and you figure out that's a zero-order elimination process, how long is it starting out at 0.23 BAC until you get down below the legal limit of 0.08? You can use this relationship in order to figure that out. So you could either use this to figure out time, you could do 0.08 over here, and then we can figure out time if we knew our rate constant K. You guys see how that could help? So if we know something about that person and how quickly their body metabolizes ethanol, then that's our rate constant K. And then from that, we could say, well, I know how much I started with. I know what I need to get to before I'll be legally allowed to drive. And I can figure out the time. Or, if I give you the amount of time, I say, well, you waited 2 hours before you drove. What would your BAC be when you left? You could also use this equation to calculate that. So the integrated rate law is a way that using the derivative of the plot of concentration versus time, we can actually use that to figure out how time influences a change in concentration. So what we're looking at is this integrated rate law here, the one that actually says integrated rate law. It's saying that the change in concentration is equal to negative KT. And what that really means is if we look at a graph of concentration versus time, that if we want to predict how changes in time influence concentration, then we plot how we can use this relationship here. What is the y-intercept on this graph? Dano? What's the y-intercept on this graph?
0. Hold up, and initial concentration.
Okay, so whatever the initial concentration is, that's what your BAC is at the time your body starts getting rid of it. And then we say, well, how does that change over time? That's our rate constant. That's our K. That's our body's ability to do that. And it might change between two different people that have different amounts of an enzyme that does that. And then time is our X variable. Change in concentration is our Y. Okay, so what we're trying to show you here is that there's multiple ways of using the concentration versus time graph in order to get information out that lets us predict what the rate is going to be and also how it changes, concentration changes with time. So let's take a look at first order. So if we have a first order reaction, we can do the same thing. We can say, well, looking at that data, I'm not quite sure if it's first or second order. So I can calculate all the values for 1 over concentration, natural log of concentration, and I can plot all three of those. When we plot all three of those, what trends do you guys see? Sarah, what trend do you see from these three plots? Jose, what do you see?
The first order is a linear relationship.
All three of them are linear?
No, first order.
Okay, so this is a first order graph. So what's a linear relationship in a first order? What plot? So we have 3 plots up here. We have radioactivity versus time, natural log of radioactivity. Okay. So whenever we have something first order, we see the plot of natural log versus time gives us a linear relationship. What can we do now? What do we know? What does that help us with? We know what?
Y value, X value.
Okay, so we know that if we have a y versus x plot of natural log versus time, that's a linear relationship. So as well as, so we have this funky integrated rate law, but let's do this instead. I think it's way easier to do this. So the integrated rate law is a not very nice formula that they typically show you in the book. So I don't want you guys to write that down. Write down the straight line formula. See, this is how it works. Is that chemists, we like to find trends. Trends that allow us to make predictions that are usually y equals mx plus b. Does anyone see the y equals mx plus b in this formula? What is our y? Natural log of the concentration at time t. What is our m, our slope? Negative k. So if we know the slope of the graph, do we know our rate constant? Okay. What is our y-intercept? Brooke. So if this is a y equals mx plus b equation, what's our y-intercept? ln of our initial concentration. And Katie, what's our x value? Time. So if we plot this, if we take the data and we transfer all of the concentration and we do natural log of every single one of those, and we plot every one of those points, natural log of concentration times 0, time 1, 2, 3, 4, 5. We get all of these times, and we find that they make a linear relationship of a plot where the intersection with the y-axis is the natural log of the initial concentration. Slope of that graph, I have a lot of students asking this question. Is the slope of the graph k or negative k? How do we know? What is k sometimes negative, sometimes positive? What is it? It's always positive. So what's really nice about this is that you can always look at this and I'll be like, I know the slope is k. It's the absolute value of the slope. Just do it that way and it'll be really easy. And then you have your change in concentration can be figured out at any point in time. Tom, you have a question? So we see a negative slope here. And we know that our rate constant is always positive. So same thing with the last one, 0 order. It was a negative slope, right? K is our slope, but the absolute value of the slope. Does that work? Because, so if you use rule of logs, you can rearrange this equation into this one. Because rule of logs, when you invert something, then you change the sign of it. And you can go through a derivation if you want. I'm not using our class time to do that today, though. Okay? What about second order? What relationship are we going to find to be a linear relationship for second order? So let's look at a second order graph here. So we have a whole bunch of information. We want to know at 42 hours. We have a whole bunch of information. If we plot all 3 of these graphs, only one of them is a straight line. So why did I say the absolute value instead of the opposite sign of like negative k? What's the slope here? Is it positive or negative? Okay. So we're always looking to find the slope of any one of these graphs that is linear, that represents that equation, that relationship best. So if we dig into second order then, We have our second order rate law, differentiated rate law, but this one only tells us about the rate of the reaction versus initial concentration. We want to know more than that. So if we rearrange these equations into a linear format for us chemists that hate figuring out exponential relationships, if you were to only plot 1 over the concentration at any time versus time, then this is the equation of the line. So what we're trying to do is find ways to predict how concentration changes with time. And if we know it's a 0 order, first order, second order, then we can make predictions based on equations that fit specifically to those. Does that mean that K is going to be the same for anything the second order? No, unless all of them have the exact same slope, which doesn't happen at all. So this is what a plot of a second order reaction looks like if you plot 1 over concentration versus time. Pat, what's the y-intercept for a graph like this? 1 over the initial concentration. Sabrina, what's the slope of the graph? Our rate constant K. And this equation here allows us to make some predictions. How concentration changes with time. I think let's try using some of these. I think that might help. And there's also a way you can predict half-life. We're going to get into that a bit more in class on Thursday. Okay? So why don't you guys go ahead and click in what rate order this reaction is. What would be more useful than this to help you guys figure it out? So let me do some calculations, and then I'll show you guys graphs. Question, Kurt? Or you want to answer it? All right. What's your question?
How does all of this relate to what we did in class on Thursday, where we had like rate orders and stuff that was like determining like a molecule's rate order was completely different than what we're doing now?
Okay,
That's what's throwing me off.
So there's two. That's a really good question. So there's two ways to talk about a reaction. What if I want to know what's the rate of the reaction if I start with 2 moles versus 8 moles? Does this help me at all? Not really. I mean, I could plot it and I could backtrack to figure out what the slope might be. That's a pain. So what equation could I use? What relationship can I use to figure out how the rate of a reaction changes given a different initial concentration? So the question is, if I want to know how the initial rate of a reaction changes based on concentration, am I going to use integrated rate laws? What am I going to use? The differentiated rate law. So we have 2 rate laws now. One that compares concentration with initial rate. That's what we figured out last Thursday. This one, it isn't about the rate versus initial concentration. What is this one allowing us to look at? What variables are we looking at here? Time. Differential rate laws don't have time. This one now has time. And we can look at, well, if we started with this, what are we going to end with? Or how long will it take to get to a certain point? The same rate orders, though. Second rate order, it means that we can do either one of those now. It means now we're in the middle and we can look at either side. How is the concentration going to affect the rate? Or how is the rate going to change with time? And what's the final concentration we get to? Does that help answer your question? Okay, so what did everybody say for this one? Almost everybody says first order. Why? Demetrius, did you say first order? All right. Chelsea, what did you say and why? Because it's linear. There's 3 plots there. Not all of them are linear. Salma?
I said, similar to what Chelsea said, because I know the first order shows like a linear
First order shows a linear decrease in what graph? Careful, don't say the first one. We need to look at the units. Taylor?
I was gonna say, first order for, I think, the natural log over time.
So I intentionally switched the order of the graphs in all of these, so you don't just say, well, if the one on the left is linear, then it's zero order. The one in the middle is linear, it's first order. The one on the right is linear, it's second order. You guys need to be looking at more details than that. So in this one, only one of the three plots of concentration versus time, natural log of concentration versus time, and 1 over concentration versus time gave us a linear relationship. That implies, here's the thing that I always struggle with, is do we go through the calculus in order to prove these to you guys, or do you just want to use what people have found? Okay, you want to spend the rest of the class in calculus? Okay, so our book goes into this, and it steps through how these are derived. So if you want to go through and read that, and to convince yourself, please do. The trends that I'm asking you guys to be able to use are, if one of these plots is linear, which it should be for our class, we're not doing a rate order of 1.5. It exists, we're not going to do it. Then you guys should be able to say, well, I know the natural log of concentration versus time is linear, and so I know this is going to be first order. How else do we know this graph is first order? This reaction was first order? Pat?
Because it's radioactivity.
Yeah. So any radioactive decay is always going to be first order. So those two things should have been keys, even without doing this manipulation that we did. All right, what about this graph here? Talk to your neighbors. You also have the data on the back of your worksheet. On the back page, please sketch out what these three graphs look like. You have 3 blanks. Sketch what the graphs look like, and then make your decision.
No, you're
doing.
I kind of want
changes.
Yeah, I kind of want
You're welcome to. Or you can look up at the screen because I just plotted them. But it's up to you. Megan, you ready to explain this one? So I do suggest that you guys fill in these on the back, and that's that same table of data.
I have a question.
What's that?
Anytime it's linear, for a certain graph, like say if it's linear over concentration at the time, that will be 0.
Always.
Always. Okay.
Because then the other two graphs won't be linear. All right, a couple more seconds. All right, Megan, can you share your thought process on this one?
Well, I looked at the 1 over the concentration in relationship to time, and that was linear. So when that happened, it's second order.
Did anyone figure that out before I showed the other 2 plots? Kirk, how'd you figure it out?
I was just did math on my calculator.
What math?
I took the, like for the time increase from 0 to 100, I took the 1 over NO2 value 154 and subtracted 100, and I did that for all of them, and found that it was like relatively the same change between each each 100 seconds. So if it had to be linear, or relatively linear.
So going back to what Brianna said, she noticed the trends in each one of these. So we know that a linear graph means that as x changes, y changes by the proportional amount every single time. So the same amount, right? And if we look at the other two columns, we would have seen that these are not linear because that difference every time, the change in time is the same. It's 100 seconds, 100 seconds, 100 seconds, 100 seconds. And we notice that there's not an equivalent change in natural log of concentration for each one of those steps, or concentration versus each one of those steps. So I like it. You can use either one of those. That's fine. If you can answer either one of those in my class, then you have done what I have asked you to. So that means that we have, come on. That's awesome. Good job, guys. Miata, question?
So if there's a linear relationship between concentration and time, does that mean that the rate order is 0?
Always.
Okay.
Yep. So anytime we see a zero order reaction, concentration versus time will be linear. We didn't see that here, so we know it's not linear. Not zero order. Sorry. And now, because we know that, we can now make predictions based on how time will influence concentration, and we could also make predictions of how the initial rate of reaction will differ with different concentrations. Demetrius, you have a question? Okay. So why do we care? Anybody care? Anybody have an idea why we might care? Don, looks like you want to share your thoughts. Taylor?
With, the rate of decomposition of like certain drugs in someone's body, we could use that to
Find out how long it takes to decompose. This is one of the byproducts of combustion. This is smog. Why do we care about smog? Why would we want to use this equation for smog? What's that? Well, if we want to measure it, we'll put an instrument outside. So what does this allow us to do, though? What's that, Alex?
The rate at which it's like forming.
Not exactly the rate. That's not what we use this equation for. Don?
Is it gives them how long they have to process it before they release it?
So this is just how fast the reaction happens naturally in the environment. So if there's a smog alert, which we don't have here in Delaware, but there's a lot of cities that do have smog alerts where you're not supposed to go outside at certain times of the day because there's too much smog outside. What does this equation allow us to do?
We can calculate like how long you have to stay inside before the smoke clears enough for it to be safe.
Yep. So we can start thinking about how long until it's a safe concentration outside. So let's do that. All right. How long from the start of this exact reaction, right? Time 0 is shown here in the table. How long until this reaction reaches the concentration of 1 times 10 to the negative third molar? Take about a minute, try to think about how to solve this, and then we'll come back together to work through it a little bit more. What are you thinking?
Like plug into the rate order.
Okay. So what goes where?
The initial concentration of NO2. This times 10 to the negative third, and then you're looking for the time.
Looking for the time. But what is this? We don't have that.
No.
Like if we use the first, like if we use 0 and 100, we use those two concentrations.
For the second order. Yeah. It's like at 100 seconds, 200 seconds, 300 seconds. And then
So why are you putting in, what are you solving for?
I solved for my K first, and then I went and I plugged it into this one.
Okay. Yeah, so it's not.
Okay, sig figs is gonna be all screwed up.
Yeah, but remember it's addition, right? So whatever
No,
you
'cause
get
you're
here.
dividing.
Oh, you are in
You'd be
the end.
dividing by
Yeah, you are. So let's use 3 for this for now.
I can't figure out,
Yeah.
can't remember how to find it.
All right, so let's bring everyone back together. What's the missing link? We don't have a rate constant k. Can we find it? How do we find the rate constant, McKenna? Okay. Claudia, how do we find the rate constant? Mia. Why are you looking at the change in 1 over concentration versus time? Love it. From the integrated rate law, we know that the slope of the graph of 1 over concentration versus time is our rate constant. That's one way to find it. Did anyone else find our rate constant another way? There's another way to find the rate constant. Who found it? What about the line formula?
Do 1 over AT is equal to KT, 1 over AL, you can find your K value.
1 over AT equals KT plus 1 over, I guess we can do, we did A, right? So if we know everything, if we use one of our data points, can't we find our rate constant here? If we plug everything in at t equals 100, could you guys find your rate constant? So do that. Find your rate constant and then click in. Use that rate constant then to find what the time is to reach this concentration. What's that?
I got 522.
How?
Well, I solved for K, and I have it stored here for this by taking. I think I might know why. You're not supposed to use 0 when you calculate it, right?
Well, if that's your initial concentration, so you
Yeah,
need to
so
look
I
at what you're
did-
comparing.
Yeah, I did these two.
Okay? So
Compare
then the
these
change
two.
in time is 100. Change in concentration is whatever the difference between those two
Yep.
is.
I did that.
So this is initial and final. And you should be able to find it.
We'll do it again.
What'd you get for your rate constant?
I got 0.5 and I got 0.0709.
What points did you use? Different points?
Yeah, he went 0 to 100, I went 0 to 6. And then I went 100 to
What did you have for your T then?
T, I had 600.
Okay. So after 600 seconds, so you guys should have exactly the same.
Yeah, we should have something.
So somewhere you, what is that?
That's 10 negative 2.
What is that?
1 point, or 1 point at a time, 10 to the negative 2.
Go back to your equation. You're using,
Oh,
you
I'm
should be using
stupid.
these numbers,
Yeah,
or
I see what I did.
you're flipping things around.
And then I got K 25. So, 900 equals 0.55 T. Divided by 7.55, and I got
Yes.
1636 point whatever seconds. Three significant figures, I got 16 points.
And then I add initial concentration.
Concentration is 100. 1 over initial concentration. And then K times time. And you solve for time.
Okay, and I got all in because
Does that seem like a lot? Look at your data.
Yeah, so this 1 over K. So I'm confused why you got 0.3.
Talk through it.
Oh, it's because it did 1 over 1. Like, I don't know if your calculator can do it, but my negative stuff.
So you need to write these
I always
numbers
do
out
like that because
to see where the zeros are and what your final concentration versus initial is. Because I think you're flipping things with a negative exponent. Careful. Careful. What is supposed to be in the bottom of the second order?
The concentration.
Where did you get that number? Point before you got that number. What is that? Two numbers. Look at that column. Look at the column. Where's the concentration? Which column is concentration? This is already 1 over. So you're doing 1 over 1 over. Let's do about another 20 seconds to finish up your thoughts. So I've seen a lot of people doing the same mistake. A lot of people are plugging in 1 over 100 for times 0. Why is that wrong? Times 0, the initial concentration. So for initial concentration, people are plugging in 1 over 100. Alex?
Because they actually give you the 1 over the concentration, that's not just the concentration.
So people are using the 1 over to plug in the 1 over. You can't do 1 over concentration. Either you do 100 as your initial concentration, or you do 1 over the initial concentration, which is 1.00 times 10 to the negative second molar. Do you see the difference between those two? Did anyone else do that? Okay. So make sure you're using the values that are appropriate for where you're using. All right, so what did you guys find for your rate constant K? Tatiana, what is your rate constant K? 0.5 for... Any more? 544? Okay, what should our units be? Anybody units? Tatiana?
1 over m times s.
1 over m times s. Everybody agree? Anyone have something different? Alex?
Question, because I used the 1 over the concentration of NO2, and 154 is different from 1 over 6.48 times 10 to the negative 3. So what do you want? Like,
What?
Like it's rounded for 1 over concentration.
Oh.
So what do you want us to use?
Well, it's reported as 3 sig figs.
Okay.
So if you want to be more accurate, then you would probably do 1 over the concentration instead of using the 1 over value you're provided with.
Okay.
That would be better. Does anyone disagree with the units here? For rate constant K. Mommy, what did you have for your units for rate constant?
I had 0.514 and then the m to the negative 1.
So everyone has m to the negative 1, s to the negative 1. Okay, so I realize I'm digging myself in a hole here, and this is not a good place to be harping on this. Okay, so if it's second order, we know that our rate equals our rate constant times concentration, in this case NO2 squared. We know that the left side is molar per second. We know that the right side is molar squared times some units. In order to get those equal to each other, we need 1 over molar times seconds. What's annoying is that it doesn't really work out in the integrated equation, right? That the units in the integrated equation end up being all screwy. All right. So let me dig myself back out of that hole that I didn't really mean to get into in the first place. Okay, so I agree with your units, Tatiana. Thank you. And then how do we use this to solve for the time? Sabrina, can you share how you use this rate constant?
I'm sorry, what's the question?
How did you use the rate constant that we have?
Well,
times time, which we were trying to figure out, oops, plus initial concentration, right? 1 over 1.00 times 10 to the negative second molar. And then we can solve for time. What's up, Val?
I have a question about K. So, do we find K based on the table or just looking at the graph?
You could do, so I wouldn't just look at the graph, unless I would always use the graph to say that's a linear relationship. If it were me, I would say that the slope of this graph would be change in time in relation to change in 1 over concentration.
Because whenever I did it between different intervals of 100 seconds, I get different values.
How different are they?
It was different. It would range from 0.5 to 0.87.
Did everybody find that?
Am I doing this really wrong?
I don't know if I'm doing it wrong either, but I got 1.85, and when I did it for each one, I got close to 1.85.
So 1.85 is too far off. I wouldn't be surprised if it was 0.6, 0.7, 0.5, but it shouldn't be anywhere near that big. So what's the most important way to find this, the best way to find the slope of any graph, if it's linear? Do we choose 2 points that are close together? We choose 2 points as far apart as possible in a linear range of the graph. So if it were me, I would use the slope of this graph is going to be the change in 1 over NO2. So 426 minus 100 over the change in time is 600 seconds. And then if we do that, then it's 326 over 600 seconds. What is that ratio? Okay, so it might have been, Don, that you flipped that? Okay, so we need to make sure it's the slope of the graph. Yeah, I mean, just think about any time you do a graph. Are you going to find the slope of a little tiny segment, or are you going to use as much data as you have to find a bigger, more clean average? So it should be any point in between, there's going to be a little variability because if it's real data. But over a longer span, you're going to find a more appropriate average. Okay, and then when we solve for t, we find, see what you guys found. So we have 1660, 1650. Looks like you guys are all pretty close. If you did 0.543, which of these numbers do you come up with? Anyone use 0.543 as okay? What'd you get? But for all intents and purposes, these ones are all fine by me. What questions do you guys have? Kira?
I just don't know if I did something wrong or not, but I got 1654.412.
So that's close enough for me. So it depends on if you found your K using 2 data points that are really close together, then you're not going to get as accurate of a K value. So always try to span as much as you can within a linear range. If you see, like we're going to see some graphs that have, well, the drug gets absorbed first, and then it gets out of your system. We're not going to look at the whole graph. And we'll get into that if we have time. So you guys have already done this. We can rearrange the equation to solve for time. And the number that I ended up with using that K is 1656. And it depends on how many sig figs we want to use. But if we use 3 sig figs to find K, then that would limit it to 3. If we use 1 sig fig for K, then that would be crappy. All right, so if we're doing 3 sig figs, I'd want to see 1.66 times 10 to the third seconds. Does that number make sense, Val? So what I'm asking there is I'm asking you guys to go back to the initial data and say, well, we started out at 0.001 molar. Right? And we're saying, well, how long until we get to this concentration? That's past the end of this graph, so it should be more than 600 seconds. And we'd have to follow the graph out. If we go back to our initial graph, concentration with time changes like this, and so it looks like it's going to take a while to get to that final concentration. Okay? And I'm going to post these slides online afterwards. I'm just trying to summarize the differentiated and integrated rate laws so you guys have them all in one place, and that's going to be on this slide. And this slide. I have two big summaries that give you a whole bunch of information. Going back to Kurt's question, it doesn't matter how we find the rate order of reaction. All of these equations and relationships become available to us once we find that, and so we can answer a lot of different questions. All right, let's go ahead and solve this problem. So the first question was, without a catalyst, now we're saying we have a catalyst there. And now we're going to change some stuff about the reaction. So use the data that's shown here to answer this question, not any of the data we've been using up until now. Completely new question. What's the time of this one? So give it to the relative.
You guys getting there? Do you know which rate law to use? Which order? That one's for the second. So, is my okay, in the graph is negative.
Concentration doesn't change to what? What stays the same? It is really important what it is. Concentration doesn't affect the rate, but the concentration changes, right? Or else it wouldn't be a reaction.
Just like make a little bit to know what that is.
All right, so wrap up your thoughts. At least write down how you're approaching this problem. We'll talk through it.
So like when I'm solving this, I know this. Should I like do this with the negative, or should I just get? That is the seconds time.
That's not seconds. Oh, that's milliseconds. That's the period.
Yeah.
Sorry.
Yeah.
So is K positive or negative?
K is negative.
Okay.
But the value of K. I mean, it's
So, but
negative.
what's the equation now?
The equation is negative.
Okay. Demetrius, why don't you just look at me? Why don't you raise your hand? Come on, guys, help me out. You guys realize that this only works if we're doing group work in class if everyone raises their hand. Let's do it. I'm going to be really annoying here. Everybody, please, including you, Javante, Brian, Alex. Okay. If we're stopping class to do group work and letting you guys go free range to work on stuff, which I think is really going to help you guys figure out how to use these, you have to help me get back to class very quickly. So please participate in the hand raising even though you feel childish. So how do we do it? We have a whole bunch of information here. How do we sort through all this, Kira, to try to figure out how to answer this question?
So you gave us the slope, which is K, so that's negative 9.0133 times 10 to the negative fifth.
Okay, so you said I gave you the slope, which is K. Is it quite that? It's a little bit, there's a caveat there. That's the absolute value of the slope is K.
Okay.
But how do we know that? Why this graph? Is it just any graph the slope is K? Well, it kind of is. But then why is this slope? There's one big step that you skipped over before we start using K.
It's 0 order.
Zero order. How do you know that?
Because it's linear with concentration over time.
Because we have concentration versus time. We see that there's a linear decrease in the concentration over time. Then we have differentiated rate law is open to us, and we know the integrated rate law. And in that integrated rate law, we're going to need to know a rate constant, which is the absolute value of the slope. Okay? Those are the steps I want you guys to go through. So if we have our slope is the absolute value of that, then what do we do with that?
Then you can put in the other values into, I use the straight line form.
Okay, so the concentration at time t is equal to?
Is equal to the constant K times time plus the concentration of 0.
plus the initial concentration. Is that what it is? What's the initial concentration here?
16.9.
Everybody agrees? 16.9 times 10 to the what? Negative 6 molar. Okay, so that micro is really important. And for our seconds. We actually didn't even write that in there, did we? So when we write in our seconds, we have to do 0.150 seconds because that's 150 milliseconds. Okay. Yeah?
Do you still use negative K because I think negative K?
Absolutely. So that negative out front is really important because otherwise, and here's, can I give you like some really stupid advice? It's like it sounds so obvious, it's really dumb. If a reactant is being consumed, should the final concentration be greater or less than initial? We're using it up, it's going away, right? So if we don't have a negative KT, then as time gets bigger, we have more concentration. That doesn't make any sense. So think about your calculations as you're walking through them. And I want to say that I have these guys all written out here. And so I found that the final concentration is down about 3.38 micromolar. And it looks like some people were off with their answers. 3.38
Do you want the answer in micro?
times 10 to the negative 6. Okay, guys, help me focus. We have 2 minutes left. What questions do you guys have? Are there any questions? We need to be able to use this equation to solve for time. We need to use this equation to be able to solve for final concentration. So I have another couple problems in here that you guys can work through on your own. And they are solved, so you can click through them. And the big thing that we want you to be able to do, and we're going to have to do this at the beginning of class on Thursday, is we're going to do the overdose thing. We're going to say that if you overdose on a drug, how long until you're safe, until you're in the clear? Okay? That's going to be exactly what we're talking about. From real drug data, we're going to be determining the rate order, deciding whether a patient should go to the hospital or not, looking at data like this. So what questions do you guys still have? Alex, you got a question?
No, I figured it out.
I have a question.
Devontae?
I don't know when to use the absolute value of K or when to use the actual value.
Okay, so when we're finding our rate constant is always going to be a positive number. But depending on which integrated rate law you use, you're always going to be detracting from the total concentration. So make sure you pay close attention to what the integrated rate law says if you're using a positive or negative. Some of them it's a positive K, some of them it's a negative K. So make sure you have those integrated rate laws memorized, written down on your note card for the exam, however you want to use it. All right, we'll do some more on this in class on Thursday. Thanks, guys.